Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list, published on September 16, 2025, about 4 days ago. The standout result is that coordinated defenses can tame a new threat called compositional privacy leakage, with collaborative consensus defense reaching roughly 86 to 90% sensitive blocking, while keeping about 66 to 70% benign success. The paper is titled, "The Sum Leaks More Than Its Parts, Compositional Privacy Risks and Mitigations in Multi-Agent Collaboration." And as we will see later, the implications for real deployments are quite significant. The study formalizes the attack, evaluates theory of mind and collaboration strategies, and shows collaboration offers the best privacy utility balance. On X, posts stress that harmless answers from different agents can combine to reveal sensitive details, and they highlight theory of mind and collaborative consensus defenses. Engagement looks moderate, with dozens of likes and replies. The previous segment highlighted strong blocking with collaboration. Figure 1 illustrates how an adversary composes harmless fragments from 3 defenders to reconstruct a sensitive fact, because each table maps different links like customer to name, product to ID, and claim to ID. The chain of thought row shows unrestricted sharing that enables leakage. The theory of mind defense shows agents judging intent and withholding risky pieces. The collaborative consensus defense shows agents coordinating and voting to block combinations that become sensitive. Alright, the previous figure introduced the attack pipeline. Figure 2 contrasts 4 defenses side by side, showing how information flows and when replies get blocked. The chain of thought panel keeps reasoning local, which leaves gaps that an adversary can exploit. The theory of mind panel adds intent estimation from knowledge, sensitive sets, and query history, so risky queries get denied. The self-voting panel bases a single agent's decision on a shared state. The collaborative consensus panel aggregates peers and blocks if any vote says block. So, the previous figure contrasted the defense architectures, and Table 1 now spells out the defender policies with their inputs and behaviors. The chain of thought row limits itself to local knowledge, which leaves no awareness of sensitive combinations or histories. Chain of thought with sensitive set adds rules to block risky fragments, and adding query history extends that to sequential leakage. Theory of mind simulates the adversary's evolving knowledge to deny enabling steps. Collaborative consensus shares aggregated state and blocks if any peer flags high risk, while self-voting samples multiple internal votes. So the previous table defined the policies, and Table 2 reports how they performed across models. The table summarizes sensitive blocking, benign success, balanced outcome, and overall success, which together show the privacy utility trade-off. For QN332B, self-voting achieved the highest sensitive blocking at 97.1%, while collaborative consensus led benign success at 70.2%. For Gemini 2.5 Pro, collaborative consensus topped balanced outcome at 79.8%. For GPT-5, theory of mind maximized blocking at 94.2%, and collaborative consensus delivered the strongest benign success at 66.3%. Alright, the previous table quantified overall outcomes, and Figure 4 breaks down plan execution for benign versus sensitive runs. The 3 panels compare defenses by how often the adversary completed its planned steps, which indicates leakage risk when the run was sensitive. Chain of thought shows high execution for both classes, so leakage remains likely. Theory of mind and collaborative consensus keep sensitive execution near zero, while preserving moderate benign progress, which signals a better privacy utility balance. Self-voting sits between those extremes. Well, the previous figure dissected plan execution, and Figure 3 highlights how deep the defenders reasoned on Gemini. Figure 3 shows the fraction of responses at depth 0 through depth 3+ across 6 settings, which clarifies whether policies engage shallow or multi-step reasoning. Chain of thought variants stay mostly at depth 0, so they rarely consider downstream consequences. Theory of mind shifts mass to depth 3+, indicating proactive intent modeling. Self-voting and collaborative consensus display balanced depth 1 to depth 3+ distributions, which supports their privacy utility trade-off. Alright, the previous figure analyzed reasoning depth, and Figure 5 illustrates a step-by-step adversarial run across 3 defenses. The left column shows chain of thought answering each query, which lets the attacker stitch flight, payment, names, and approvals into a sensitive final inference. The middle column adds theory of mind, which flags intent at steps 2 through 4 and blocks the enabling replies, so the final inference omits payment. The right column applies collaborative consensus, where peer votes block risky steps and the final output stays safely partial. Alright, 2 takeaways stand out. First, small harmless answers can combine into a sensitive reveal, so single-agent safeguards miss real risk. Second, coordinated defenses, especially collaborative consensus, deliver the best privacy utility balance compared with pure chain of thought or theory of mind alone. The broader implication is clear. Multi-agent deployments need collective, intent-aware controls. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.